I do prototyping engineering at this company as a mechanical engineer. I also do some machining. That's part of my job. Has anyone been in a machine shop? I highly recommend to the people who are running this program that you at some point take people through a machine shop, because I think everybody should know how actual stuff is made. And a lot of actual stuff is made in machine shops. And I had no idea about that world until I ended up getting a cool internship. And I sort of wish that I had known more. I think it'll be useful to any of you, even if all you do is program. What?
I actually am really interested in that, but I've been having trouble finding info on making actual things. Do you have any suggestions that you know Wikipedia?
I know in the Bay Area there's this thing called TechSpace or Tech Shop, where you can go and just get training and take classes. Tech Shop, I think it's called. Shop, like machine shop, S-H-O-P shop. But you are, right now, you're at a university. I am sure there are a bunch of machine shops at this university. So anybody who is associated with this place, you can probably ask around and say, hey, could you just, show me the shop? Or, who here has a connection to the, mechanical engineering shop? I'm sure there's one. So I would ask your partner facilitators. But yeah, the shops are cool, and building stuff for real is really cool. So I'm going to talk about 3 things that are kind of maybe related, but kind of disjointed. The first one is what I work on most of the time for my real job, which is a monumental clock. And we'll get to that in a second. The second one is my hobby, which is the robot violence part. And then the third part is just advice that I have as a wise woman of engineering. So the first thing I want to talk about is my day job, which I think is really cool. And I feel really lucky that I have this job, and it's building a monumental clock. This is a clock that's supposed to last for 10,000 years and tell time for 10,000 years.
Big time project? I heard it was called the long time project?
This clock is sort of by a foundation called the Long Now Foundation.
Oh,
so,
yeah, I've heard that one.
Yeah. So the idea here is basically most of the machines that we build, if you think of your smartphone or your computer or whatever, they're all designed to basically be obsolete in 5 years. Most machines that we build, we don't build for longevity. But there's sort of no reason why that is. We have the capability to build things that really could last a long time. Building a machine that is functional and functions continuously for 10,000 years is challenging, but it's not that far out of the realm of possibility. And it's something that we have stopped kind of thinking about as a culture. It's sort of oh my gosh, check Twitter again, wow, what's happened in the last 5 seconds. And so this foundation that we're working with, that I'm working for, wants to get people to try and think about the long term more. What's going to be important in 100 years? Is it a new app for, I don't know, whatever fancy version of Instagram is next? Maybe in 100 years that won't be important. But maybe working on, I don't know, jetpacks or going to Mars or what those things, that's probably going to still be important in 100 years. So they're trying to get people to think about the long term. And part of how they're doing that is building this functional monument, this functioning machine that's supposed to last for 10,000 years and tell time for 10,000 years.
What's it called again?
Either the 10,000-year clock or the clock of the long now. It gets it gets a lot of different names. So this is it's a monumental clock. Part of how you make something last for a long time is you make it big, so that if you get a little bit of rust on it, it's kind of not that big a deal. If you had a little baby clock like this and it got a little film of rust on it, that would probably jam the gears of the clock and it wouldn't work. But if you made it really big, then you get a little bit of rust and it doesn't matter. So it's really big. It's going inside of a mountain. It's going inside of a vertical bore in this mountain, which is in West Texas. It's a very dry area, which is also really nice. Humidity in the air is one of our big concerns for this clock, which is all mechanical. So a lot of people sort of say, well, why don't you just make an electronic clock? The reason why not to make an electronic clock is that electronics that depend on semiconductors have doping in them. So they use silicon, which is kind of one thing, and they bombard that silicon with certain other elements to get p-doped or n-doped semiconductors that behave in certain ways, and then you make transistors out of these things. But over time, the doping in a semiconductor will diffuse out, and transistors just sort of stop working. So a lot of, you think, oh yeah, like I put it on the internet, it's there forever. I put it on a storage device, it's there forever. It's not really true. Devices that depend on transistors, basically, they have a lifespan in the decades. It's maybe, lots of decades. Maybe it's 5 decades. Maybe it's 8 decades. But over the course of that time, physically, like the chemicals that are in those chips will stop working. So this is an all-mechanical clock. It's made out of stainless steel and titanium. It goes in a vertical bore inside of this mountain, which keeps the temperature very constant, which is also good for fatigue. If you get something hot, then you cold, hot, cold, hot, cold, hot, cold. That's the way that a lot of things fail. So like concrete that gets cracked, often that's because it's gotten hot and cold too much, or it's because there's tree roots. But when you're looking at a mountain, you also want to make sure that your mountain is really geologically stable. So if you're like putting something in the mountain for a year, like whatever, it's a mountain, it'll be good. But if it's 10,000 years, you want to look at the rock and say, like, is this rock of a quality that it's not going to flake away and break down in 10,000 years? Kind of a question you don't think about that often. So here are some rock core samples that we did of this mountain. Here's the work site out at this mountain in Texas. And then here's a lot of the earth-moving equipment. So if any of you are interested in construction or civil engineering, I got to say, it seems like a really cool job. That's not my job, but you get to work with some cool machines. This one, you can see it's got these weird tips. When they're doing rock work in the kind of limestone that we have, they don't use anything sharp. They just use these blunt objects, and they press them really hard into the rock, and that causes the rock to just sort of spall apart. And that's how they work rock. There's so much like interesting engineering knowledge in how to do things like that. Like, it's not something we think about a lot, but I encourage you guys to consider careers in civil engineering, because I think it's neat stuff. Yeah? Oh, sweet. Yeah.
I'm really interested in buffers and longevity. And I found out a long-time project by hearing about the 2038 problem and looking at really long clocks. 0 to 2038 problem, basically Unix clocks on 32-bit PCs stop at around 2038.
Yeah. Yeah, so the problem that I think you're describing is sort of like, you guys are too young to remember this, but also like the Y2K problem. Like, oh, we didn't think about when we like roll over on a digit that like is too far away to ever roll over on. Like when you went from 1989 to 2000, you had this problem where like everything was coded just to have like the 2-digit year. So, but then when you go to 2000, like suddenly you're not in 1901, you're not in 1900, you're in 2000. Like, what do you do when you haven't made a plan for 100 years worth of timekeeping? So this clock actually has an extra 0 in front of all of its dates. So we write our dates in a 10,000-year compliant format, so that when it's 3,000, when it's 4,000, when it's 10,000, when it's 11,000, we have that extra digit available. So anyways, here's a lot of different pictures of cool earth moving that you could potentially be a part of if that was a field that you wanted to go into. Mining, blasting, and explosives, pretty cool. This is them blasting the side access tunnel into this mountain. Here you can see all of these lines are where they've drilled a hole and then filled it with dynamite and then blasted away. We found a cool natural cave. Sometimes you find sweet caves when you're doing mining work. Here's what it looks like if you visit the site. And what's that?
Is that all from glass?
Yeah. So all of this stuff that looks like a tunnel is all blasted out. And then in order to make this vertical bore that this clock is going to sit in, we used a boring head, a vertical boring head. That again, these teeth here, they don't even look like teeth. Those are what it actually cuts the rock with, these like little hard nubs. So here's a little video of it in action. Oops, maybe. right? Maybe not. There we go, yeah. This is it starting to cut the bore, and you pull the thing up from the bottom. You can imagine if you're trying to drill down, then all of the detritus would sort of stay in the hole. But if you like cut a tunnel into the side, and then you pull the thing up from the bottom, all of the detritus falls down, and you can just kind of like shovel it out and keep pulling the boring head up. That's also how they make tunnels for like transit stuff. Often it's like a sideways boring head, but if any of you are from Seattle, this is what like Bertha in Seattle is doing right now under Seattle. And then you get this. You get a lovely vertical bore, and then you need some way to get up to this clock. So you're like, all right, like maybe we should have some stairs, you know, and not just like make people scale the vertical bore. And we, not me, but my team designed this robot that can fit inside of the vertical bore, right? It's got to fit inside that, but it's also got to like reach out and cut a stairway. So it's got this robot arm that reaches out and it cuts stair steps like so. So see how it all can kind of fit inside that bore? It needs to move, but then it can sort of cut stair steps. So all these sort of close to physical production robots need programming. They need people like thinking of, like we had a couple of people for like years working on programming this robot saw and making sure that it didn't drift too much and double checking that it like stayed accurate while it's cutting its stair steps. So there's a lot of programming that exists, I think, in the sort of Google-like sense of it all is software, it's all on your computer. But there's also a lot of programming that exists at a very sort of low and close to hardware level that I think makes really cool stuff, like these stairs. So here are the stairs cut by a robot saw. You can see them making a spiral going upwards. Ta-da! And then there's the actual clock itself. Most of the timekeeping elements are going to go in this chamber here. It looks kind of like this. This is a laser scan of the inside of the chamber. Here's two of our rockwork guys thinking about how to blast the thing out. And then here's the schematic of the actual clock itself. The part that I work on is this gray horizontal box up there. You can't see what's in it, but it's a mechanism that calculates the Gregorian calendar, which is the calendar that we use. There have been a lot of different calendars. There's been like the Julian calendar. There's been Babylonian calendars, but the calendar that we currently use with like leap years and stuff, that's the Gregorian calendar. And then there are weird things that you find when you're doing a clock that has to last for 10,000 years that you didn't expect, like the length of the day and where the solstices are changes very slowly. And it's kind of predictable, but it's also kind of unpredictable. Like if there's a big earthquake, that affects the rotation rate of the Earth, and you get a little change in the length of the day. There's this process that happens over the course of 26,000 years called precession of the equinoxes, which is why people say like, oh yeah, you know, in 10,000 years, like the North Star will be a different star. The way that the Earth rotates with respect to the sun and the universe slightly changes when the equinoxes happen and when the solstices happen. So we have this cam here is a cam that has a little tiny follower that sits on the edge of it, and it reads off where noon is every day for 10,000 years. And you can see that it's not like just like a circle. It's changing in the sort of cam depth over the course of all this time. So we call it the equation of time cam. If you're more interested in this, you can read more about it by looking at the long now. And then we have all of our gears. So remember when I said that we make like really big gears so that they don't corrode too much over time? This is one of the biggest gears. It's in the main power system. Basically, the whole clock is powered by this weight that falls very, very slowly. More about how that's wound automatically, maybe in Q&A, because it's kind of complicated. But this is one of the gears that's closest to that weight that's that's taking the gravitational potential energy out of that weight as it falls and keeping this pendulum swinging. And then we count the pendulum swings, and we know what time it is. Here are some more gears. They aren't the kind of gears usually that you're used to exactly. They're not all involute gears. There's a lot of different kinds of gears. If you're into gears, there's a whole world there. You could have a cool career designing gears. These ones are mostly cycloidal gears. There's a lot of concern directed at how do you make sure that you're staying on time. And one of the ways that we make sure that we're staying timed correctly is we have a reset mechanism that uses this lens, which is the biggest single crystal quartz lens we think in the world. There's not that much need for them, but hey, we have a need for one, so we had this one made. And this focuses sunlight on a cavity that heats up and actuates a reset. It'll either be on the equinoxes or it'll be on probably the summer solstice. So, how do you make sure you're not drifting? Well, you reset yourself every so often. Here's some more gears. This is one of the bearings that we use. I don't know if you're very familiar with bearings. There's a whole art to bearings and bearing design. We can't use a whole lot of materials. A lot of materials, we just don't think it will last for 10,000 years. But this is a ceramic called zirconia that we think will. If you've ever had cubic zirconia jewelry, anybody? Looks like diamonds. It's the fake diamond. You can get it at Claire's, $3 earrings. This is close to that. It's obviously white and not diamond looking, but it's zirconia. Here are some gears that I made that are in the calendar gear box. So many gears. You're getting the point. This is calculating the leap year and the leap century. And this, let's see if this one plays, is some testing of the, maybe? Nope. How it's going? Come on, little thing. Oh, bam. So this is a cool video of some gears in test. This is the power system of the clock. It's not all the other components, but there's a big weight that hangs off of that rack there. Lots of different people's names associated with this. They're testing the human input to the weight. So if you're a human and you visit, you can add energy to the clock by winding up this weight that stores energy. There's also an automatic system that hopefully will add energy to the clock even when no humans visit. But it's only a very, very little bit of energy every day because it depends on the temperature difference between daytime and nighttime. And it's just hard to get a lot of energy out of that. So if you visit and you want to see the displays go and you want to hear the bells ring, you have to wind it up at this human winder. A lot of ratchets. That's a ratchet to make sure that you don't accidentally drop the whole weight really, really fast. 11,000 pounds. Hundreds of feet, that would be sad times. Thank you, ratchets. Ratchets are things that make sure that you can only go in one direction. You can't tell, but those are both smaller in diameter than that vertical bore that I showed earlier. They're really into this ratchet. It's the same ratchet. There are some involute gears, for those of you who know what involute gears are. They're gears where each side of the pair looks the same. There's also a lot of gears where the one side looks really different from the other side, many of which are actually more efficient. But involute gears are cheap to cut. So.
When it's actually running,
yeah.
Are the parts moving that fast, or is it sped up?
No, the human winder ones are. The weight will not fall that fast. The weight falls very gradually, except for when the bells are ringing. When the bells are ringing, it falls 6 inches. Basically, displays are expensive, especially in the mechanical world. Displays are very expensive. So you use a lot of energy to run a display. So if you show up and you wind it all the way to the top, it'll ring some bells. And those bells will use enough energy that the weight will drop like 6 inches over the course of a minute. But usually it's dropping like fractions of an inch a day. So if you do show up and you wind it, the human winding gears move that fast, but the weight doesn't drop that fast. So that's about the 10,000-year clock. That's a really neat mechanical engineering project. There are cool mechanical engineering projects in the world. You should go seek them out and do them, or you should come up with new ones. I also want to talk to you about a hobby of mine, which is making robots that fight other robots. So I do an event, sport, TV show thing, or I have done, which is called BattleBots. Where basically, like, you have a weight limit, and within that weight limit, and a bunch of other rules to make sure that like it looks cool on TV, a lot of which are kind of silly, but you make a robot that fights other robots and hopefully wins. Sorry? Oh, like a lot of smart things that you would think of, like, oh, let's just like get the other robot wet, and like all the electronics inside will short and like stop working because people probably haven't protected them that well. You can't do that because it doesn't look cool on TV, sadly, or various other things like that. But this side of the BattleBots poster is actually the first design that I submitted for my robot, which is called Chomp. This is the first version of Chomp. And this version was a giant crushing jaw. So between the tip of that jaw up there and this sort of lower jaw, this robot was designed to exert 30 tons of force and bite down on opponents. It didn't work that well. It was too slow. But then I made another version of Chomp, which is this one. This one's a hammering version. So instead of like biting down really, really hard, it just hammers really, really fast. And I think it's a really cool robot. I think it's a neat design. It was really fun to build. It's fun to think about a project where you can kind of control all the aspects of it. You're in charge of like, all right, well, I guess we gotta like make some armor now. Okay, like, well, I've never done that before. Well, let's try some stuff out. Or like, let's ask some people who know what they're doing. So this is how sort of Chomp started as ideas. Some buddy of mine was talking about alligator snapping turtles, which are this thing over on that side of you, whatever side that is, left, right, right. They exist in real life. They are sort of like prehistoric-looking, scary turtles. And so we decided that our robot was going to be this sort of snapping turtle that breathes fire robot. And then in real life, sometimes you need to like do some calculations. This robot is powered by a pneumatic cylinder, basically. So you fill up a cylinder with some compressed gas, and you let that gas expand, chunk, and then that's what powers the hammer throw. And if any of this looks intimidating, everything that I needed, like I found on Wikipedia on like the first page. Basically, you look at like thermodynamic expansion, and you find some like ideal gas law equations. If you've done any physics, maybe you've heard of the ideal gas law. It's all stuff that's, I want to say, like, you should do as much math as you can, and you should do as much like physics and science as you can, but also most of it, like, if you kind of remember a little bit, you can find it on Wikipedia. Like, I didn't really remember how to do expansion of gas, like, calculations to find the, like, total energy at the end of the expansion in the, like, end effector. But you really can find a lot of it on Wikipedia, like, if you get the basics down and, like, have that base. So, a lot of calculations. I did a lot of designing CAD. Has anyone used a CAD program here? Anybody? A little bit? I really love CAD. Not everybody does, but if you get into it, you can learn to make some neat stuff. And this works, and CAD works best if you actually, like, again, have access to a machine shop, and you can actually make the thing that you designed. So, like, these are all parts that I designed or some of my teammates designed, just using like 3D sketching software. So you make a sketch, and then you turn it into a box. And then you take the corner off the box, and then you add a hole, and et cetera, and then you make a real part. So first you do your calculations, and then you do your 3D design. So like this thing that's circled, That's the blue thing there. That's the pneumatic cylinder that drives this hammer. The black thing is the hammer, and it's connected to a crank. Do you guys know what like a crank is? Imagine like a choo-choo train that goes. Yeah, it's got a little like bar across the wheel. A crank is something that basically takes linear motion and makes it circular. If you mount that linear thing on something that's off-center from a circle, it ends up pushing the thing around in a circle. So this is a linear cylinder that goes back and forth, and it makes this hammer go in a circle because it's on a crank. And it doesn't actually go in a whole circle. You start behind here, and then you go wham, hit something. So you do your mechanical design, and you end up with these big spreadsheets. Like, all right, I got to make, how many parts is this? We're not even at the end of the list. We're at, part number 200. A lot of them you can usually buy if you can buy it. You usually should buy it, at least in my world. And then a lot of the parts you do have to make. So this is a picture of milling one of these parts out of our shop. This is a particularly complicated part, so we actually did stress analysis on it to make sure that it was strong enough. You can just look up figures for whatever metal or plastic you're making something out of for sort of how much stress it can take before it fails. And then you compare those to what your computer software says the stresses will be under certain conditions. And if you get red spots, then you change your model.
Okay, so what type of thing is used to make the gear? I don't know what.
To make what?
The gear.
The gear, like the gears in the clock?
No, like that gear right there.
This isn't a gear. This is actually the end of the pneumatic cylinder. But this is just a Haas mill. So CNC mill is something that, yeah, I mean, CNC is anything that's like, you don't like drive it yourself. So there's a lot of machines that like physically, like there's like a little wheel and there's a little table and you like turn the wheel and the table moves. But there are two, I would say like in any machine shop, there's kind of like two big categories of machines. In one, the tool spins really fast. You have like a circular cutting tool thing. And that spins really, really fast. And then you take the really fast spinning tool and you like drive it over into the part. And that's called milling. And then the other kind of machining, instead of the tool spinning really fast, the tool is stationary and the part spins really fast. So you like take a big hunk of like aluminum or whatever and you put it in the lathe, that machine is called, and the part spins really fast, and then you have your little tool and you like move your tool over slowly and you make cuts in the part. So anything that's like round, like you could make this, see how it's like you could have an axis through the middle and it's like all the same all around in revolution? You could make this on a lathe. It'd be hard to make on a mill. Anything that's like this, where it's like sort of all in one direction, you can like go up and down and like X and Y, this you can make on a mill. So this is a milled part. Go find a machine shop. And then this is the actual robot, the insides of the robot without the armor on it. It looks a lot like the. So this robot is 250 pounds without armor.
I thought you might have been this small.
There are events. If you're interested in making a fighting robot, there are events. Oh, I'm sorry. Microphones. There are events for robots from like 1 pound or like half a pound, all the way up to heavier than this robot. Although this is kind of on the heavy end. So you can make. Yeah, BattleBots are like big. So this is Chomp on the inside, and you can see that like it's kind of cool. I think it's really cool when you like design something in real life or on the computer, and it's kind of like, all right, like it's going to be like this. It's going to, here's the plan. It's like totally going to work out. Like I did some like pretty drawings on my computer, but you actually can make it in real life, and that looks pretty similar, right? Like the colors aren't the same, but like, it's got that big cylinder. Look at the wheels. Wheels. So there it is, Chomp in all her glory. The other machine that often you'll find in a shop that's really useful is something that can cut in 2 dimensions. So that's something like a laser cutter, where you put a sheet of material on it and it cuts something out. Or a waterjet cutter, which is the same deal. You put a sheet of material on and it uses very, very high pressure water with like fine sand in it, garnet sand, and it cuts with the water, and it just makes it like a 2D cutout, basically. And then here's Chomp in action with a flamethrower and a big hammer, hammering another robot. But even Chomp has some need for programming and real robotics. A lot of these BattleBots, people just kind of drive them on their own. But I had a couple programmer friends, one especially, who were interested in trying to make this like a smarter fighting robot. So we put this little LiDAR on the front, this thing here, and it looks out with a little line array of sensors, and it looks for distance returns. So it sends out infrared light and kind of waits for it to come back and says, all right, well, you are 30 feet away from me, and you are 10 feet away from me. And we use that to drive the robot, to help point at the opponent. This is actually a great environment for computer vision. Often with computer vision, the thing that is hard is like, oh, there's like way too many things to look at. Like, are you the target, or are you the target, or is that the target, or like, ah. But in a fighting robot context, there's one other thing in the whole arena with you, and it's your enemy. And you don't have to worry about a human being there who could get hurt. The other thing is, like, if you're making a dangerous robot that's just going to like drive around here, you got to be like really, really careful that you like don't hit some kid, right? Like that would be bad. Don't do that. But in a context where like you're specifically in like an arena that's closed off and like no humans are inside of it, you kind of don't have to be quite as totally like bomb-proof, well-checked before you can make a robot that looks for things. So here is what sort of Chomp sees. This is Chomp up here in the BattleBots arena, and then here is the readout from that little LiDAR. And these 4 sort of angle wedges are the ones where the hammer could hit. So if there was something really nearby, if the distance returns for these 4 were really close, then if the dead man switch was on, Chomp would hammer that thing. Automatical robots. And then here's my friend Jo. She's working on, I don't know what she's working on exactly, but something having to do with making Chomp hit things automatically without the human having to realize, oh, wait, like, there's something in front of me. I guess I should hammer. And then, like, by that time, you know, they're driven away. What's up?
Why was the robot like, I don't know, 1.5 times as tall as a person and not in the picture over there, and it's kind of small?
I mean, it's the same size.
Really? Then why does it look like it was taller than a person?
Sometimes photos, I guess, are deceiving. That's a deep question, man. I don't know if I have an answer for you. I mean, this is not like a short robot. This robot's like this tall. So like,
It's still pretty big.
yeah, it's a bit. I mean, it's 250 pounds, right? So like, if you're trying to lift this thing, there's like 4 people being like, oh my gosh, that looks so heavy. You know, it's not a small robot. But despite that, here's a video of. This is actually a misfire. This is what you're going to see here is like testing in a parking lot, and there's a weird hammerhead on because for some stunt we were trying to like throw a basketball. We never actually like made a hoop because like the wind conditions were like always a little bit different. It was sort of disappointing. But on this instance, we have sort of a misfire of our valve that shuts off the hammer. So like depending on how much compressed nitrogen you put in the cylinder, you get a hammer throw that's a different intensity. Usually we'd only fill the cylinder maybe like 15%, and then just like close off the valve and let that gas expand and do work, thermodynamic work, and get the energy out of the gas expanding. And that produces a pretty intense hammer throw. But with this one, the valve stuck open and it filled 100%. So it wasn't a very efficient use of the gas, but it made a big hammer throw. So this is a 250-pound robot. You can see the whole thing. Like that's like high in the air, right? So that bent the tail. Yeah, but hey, your robot's fine. You know, you design it to be hardy. You design it to be a shock absorbent robot. Anyways, we do. We didn't win at BattleBots, but we did get a cool award for trying to do a sort of technically advanced robot. You can't tell, but that's a giant bolt. That's like the head of the bolt, and there's like giant screw threads like this big. Like you could never find a nut that would go with that bolt. But that's me with the braided hairs. And then, so without any kind of transition, advice time. So I've talked about my day job. I've talked about my hobby. And then to you all, here's sort of my advice. It's not well organized. But I'm just going to go through it quick, and then maybe do questions. The first piece of advice that I have is there's a big difference between enjoying learning about something in school and liking doing it as your job. So I actually don't have a degree in mechanical engineering. I have a degree in chemistry. That's quite unusual to go into, to make a career switch like that. And part of why I have that degree in chemistry is I love learning about chemistry. I love reading about chemistry. It's like, oh my gosh, that's how an atom works. Cool, you know. But I didn't realize until most of the way through college that the actual jobs that you do if you are a chemist, whether that's research, research in a lab, research in an academic setting, or research at a pharmaceutical company or oil and gas work, were not jobs I was interested in doing. It turns out I'm not meant to do research. I'm just kind of not that into research. And a lot of people are, and that's great. It's so wonderful that there are people who are into research. I'm not that into research. And it took me so long to figure that out. I kind of thought, I went to a fancy college. I kind of thought I'd have good career counseling. And they'd be like, all right, you're majoring in chemistry. Here's what it's going to be like. We're preparing you to go out in the world and be a chemist. Here's what that's like. And I didn't figure that out. So if you possibly can, really try and figure out what the job is going to be that you're going to have after school. Because I didn't like a lot of the mechanical engineering classes as much as I liked the chemistry classes. But in hindsight, I should have taken those classes. Even though maybe the class wasn't as fun or the teacher wasn't quite as good. The career that I want to have is worth a slightly less awesome class. I mean, it just is. I also thought about majoring in English or history. I'm really glad I did not major in English and history. I love English and history. I like to read a lot of books. I like to read about history. But I can do that on my free time. And frankly, having a science degree, my job prospects are so much better. My earning prospects are so much better. And my job interestingness, I think, is a lot better. There's just a lot of cool jobs that exist if you have a really technical degree. And you can kind of pick up a lot of the book reading on the side. I mean, not to totally, I'm not saying that I could be a history professor, but unless you know you want to be a history professor, take as much math as you can, stick with the programming. That's something I wish I'd done more of. Try and figure out what the actual job at the end of the college road is, and do the thing that will get you the job that you want, not necessarily just the class that is the thing that you like to learn about. I know that's not in vogue. It's just oh, learn what you love. No, learn what is useful to you to have the future that you're going to love. Depressing as that may be. And to that point, if you can find good internships, really focus on that. That wasn't something that I realized. I got kind of lucky. I got a really cool internship at the end of my college career, but I really wish I'd focused on finding internships places that I would want to work. In a way, I think that's almost more important than classes. There's a thing that exists, and I would recommend this book, Women Don't Ask. I'd also recommend this blog post if you can find it, called A Rant About Women, to everybody here. Not just if you're a woman, specifically also if you're not white. I would highly recommend both of those things. They talk a little bit about something called stereotype threat. They talk about a bunch of stuff. But one of the things that they talk about is something called stereotype threat, which, I'm a pretty privileged lady, right? I'm white. I'm, my family is pretty well-to-do. I went to a fancy college. I basically have everything going for me except for gender. But I remember walking into a class in college. It was like the first chemistry class that wasn't like a pre-med class. The pre-med classes were pretty even, like men and women. And I walked into this chemistry class. It's the first chemistry class that wasn't pre-med. And I saw like the makeup of the class. Like the teacher wasn't even there yet. It was like 17 boys and like 3 girls or something. And I immediately started thinking like, this is going to be too hard for me. I'm going to do poorly. Like, I should change my major. Like, I can't do this. It's just because my brain, not because anyone said anything to me, but like my brain knew all these stereotypes about women in technical fields. And thank goodness I'd read this book, because I was like, wait a second. Like, the class hasn't even started. The professor hasn't even walked in. Like, why am I thinking this is going to be too hard for me? I haven't even like done the first day of class yet. And I did great in that class. And like, you guys can too. And you should know about stuff like stereotype fight if you can, because it's this sucky thing that can undermine you. You know, and if you can possibly learn to combat it or like recognize it in yourself, then like do that, because it's worth it. There's a lot to be said in this like saying of like fake it till you make it. Like, you really can a lot of the time. Like, even if you don't have 100% of the qualifications for something, you can fake it till you make it. You can, like, enthusiasm makes up for a lot. And if you're interested in something, and especially if you can like find that person who will be your mentor, a lot of the time in the working world, at least, you can kind of just say like, hey, I'm here and I'm enthusiastic, and I'm going to figure it out. Like, what's that thing? I'll like go home today and I'll look it up and I'll learn about it, and I'm going to be enthusiastic and I'm going to learn to do that thing. So just because you don't come in having 100% of the qualifications, I would say doesn't mean that you're in any way not going to be like super awesome at the thing that you're trying to do. That's most of what advice I have. I think we have like 2 minutes. Questions? You?
I'd like to say we could counteract stereotypes by saying, well, I know about stereotypes, therefore
Right.
I'm a lot better at this than everyone else, and this reverse thing.
Right, yeah. So
even though technically it doesn't mean anything, by believing something, it often makes someone more like that.
right, or just if you can identify like, oh, I'm having this thought because I have internalized sexism, or I have internalized racism, or classism, or whatever the thing is, and that's not actually true. That's just like the man getting me down. Like,
but the better thing is to realize that a lot of things are based on psychology, and that you can do quite a lot more than you might think you can do.
mm-hmm.
Even if you're way more privileged, you just believe that you can do it. Because a lot of times it is actually possible, but the only reason that it is not is because everyone's saying you cannot.
Mm-hmm. Anybody else?
It's also very useful to go by a lot of motivational people that convince you you can do things. That's actually a big thing that has to do with whether someone can do something or can't.
Other questions? No questions. You.
So what got you into doing BattleBots?
A bunch of my coworkers had done it, and it seemed really cool. It seemed like they learned a lot. So that's a point that I didn't mention is finding a project. This is something I struggle with. But if you can find a project that's really motivating to you, I would say like run with that project. Like anything that piques your interest as a hobby or like a side project that you're just interested in doing. If you can possibly make yourself like do that, like that's so useful. And I think a lot of the time we talk about like interviews and like getting a job. One of the things that is inspiring to me when I meet somebody is like they're like, hey, I have this thing I do as a side project, and like here's how passionate I am about it, and like here's all this stuff that like I learned how to do for this project. That's really compelling. And I mean it will be for you too, right? Like that's how I learned a whole bunch of new stuff that I think like A makes me like a more happy person, but B also makes me a more confident engineer.